Today we are going to do section 4.6, which is page 423, the directional derivative. Now, so far we've done partial derivatives with respect to x and y, right? But those are just derivatives in the direction of x and in the direction of y. Well, that's totally random. I mean, what if I want to take a derivative of a direction that is neither of those, right? There are plenty of other directions in 2D that we can take derivatives of, which is true. So the directional derivative is taking the derivative at any direction you want. The direction is given, let's look at the definition on this page, where the direction is given by a vector u, where u is cosine I plus cosine theta I plus sine theta j. So you use the theta to adjust the angle of turns, and then you will take the directional derivative in that particular direction. And so du, as you can see, is given by this particular formula, where you're literally taking the derivative in that direction, right? You have you move a over by h cosine theta and b over by h sine theta, and then you divide it by h and it goes to 0, and that would be the derivative in that direction. Now, so having said that, that can totally be done, especially if you know what the angle is, or yeah. So please do that. Example 4.31 as part of your homework, where you're gonna do the directional derivative from the definition. In other words, the hard way. You're gonna take derivative back from using the limits. It's cute to do that once, you know. And so please do that. Example 4.31 as part of your homework. And all right. So next, let's go to page 425. Now that you had fun in the previous example, taking the derivative the brute force way, which is not going to be simple, you know, they're like calculating derivative based on the limit definition. Now, as you can imagine, we actually have a neat trick. I mean, not trick, but a much faster way of taking derivatives. And that's theorem 4.112, where the directional derivative is the partial derivative times cosine theta x times cosine theta plus the partial derivative times sine theta. That's all you have to do, and that will give you the directional derivative. Now, the proof of that is a very nice and straightforward application of the chain rule. However, I want to mention something about this theorem. This theorem says that assuming fx, that is the partial of f with respect to x, and fy exist, then the directional derivative is this thing. That is not true. Okay, the directional derivative is just because fx and fy exist doesn't mean that the other direction is going to be given by that equation. That is only true if the function f is differentiable. Why? Because if you look at the proof, very soon you see that they apply the chain rule. Now, if you remember, the chain rule requires everything to be perfect. The f is differentiable, the x is differentiable, everything's differentiable. So just having fx and fy is not good enough. In fact, in the previous section, we mentioned several times this example that has a fold in it, right? Let me show you the example. Now, this is what I'm talking about. This is on page 393. You don't have to flip back and look. You just take a look at this. Now, this particular function is 0 all the way along x and y axis. Okay, and as a result, the partial derivatives exist along both axes, and they're 0. However, because there's a fold, this thing is not differentiable, and therefore the gradient doesn't work that way. That is, the gradient, if it based on this theorem, if we were to believe it, it says the gradient is dependent on the two zeros. Then the gradient is 0 everywhere, but it's not. Okay, why? Because it has a fold at the origin. As you can see, it folds some other direction. The gradient is not 0, depending on which way you point. So that's what I mean by this function says that fx and fy has to exist. No. F has to be differentiable, okay? And so does everything else involved. Everything needs to be differentiable to apply the chain rule. Now that we have taken care of that little bit of detail, okay, that everything needs to be differentiable, in reality, of course, this is a basic math class, and you're not going to deal with many things that isn't differentiable. So this is probably not a big concern. And so the proof is very nice and straightforward, a cute little proof that using the chain rule. So please do the proof as part of your homework. Now notice that in doing the proof, your book has x. First, your book says x equal to a plus t cosine theta, right? And then later it says when t is 0, x is x0. No, please replace the x0 as a. It says right here. When t is 0, x is a, not x0. Once you replace that, then the answer will all come out nicely and not have confusion of a and x0, okay? Just every x0 is a and every y0 is b. And then you can follow the proof nicely. Anyway, please try to prove that yourself, following the book's direction. And get through this proof by yourself, because it's a neat little proof with a neat little application of the chain rule. And after you do that, then the next thing is doing example 4.32, which is the same problem as 4.31, except now you're going to do it the easy way, taking the derivative instead of the hard way, calculating the limit. So now you will please do example 4.32 as part of your homework. Next, let's go to page 427, where we consider the concept called the gradient. Now, gradient is based on this thing right here. Now, if you look at our directional derivative that we just looked at, okay, it equals to this thing, which is nice. We can redefine this thing as by defining this particular vector, and that is the upside down triangle, which the gradient, okay? The upside down, well, I'll pronounce it as grad probably. So grad of f of xy, we'll define it as something as just the partial derivatives. In other words, fx, okay? And then I plus fy and of j. The reason then is that the reason of defining the gradient, grad f, is that you notice that then what is the directional derivative? It happens to be the grad of dot u, right? So grad of dot u equals to the du of f, right? It's just see, that's by the definition. So we can take you can take the dot product and as a shorthand form of expressing the directional derivative. And this thing is defined as the gradient, okay, the grad f. And the upside down triangle is also pronounced as del, or even as your book calls it, nabla. I will probably call it del or grad f. I'm not going to call it nabla. Ugh. Anyway, yeah, forget nabla. Anyway, so having said that, as you can see, grad f is defined readily, just the partial derivatives of x times I, partial derivative of y times j, and it is a vector that points into some direction, the gradient. So please do example 4.33, where you'll find some gradients as part of your homework.